Hello? 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 Okay, cool. Hello? Am I still audible? Okay, cool. Can we start? Can we start? Okay. So, Venkatesh couldn't be here today because there's some protests going around the city. So, I'll be taking today's class. Hopefully, Venkatesh will continue from tomorrow. Okay, so he told me that I should be starting with branching. He said that he had given you some 10-minute introduction to branching, but he told me that I can start over it again. So we're gonna do branching, which is also called bounded search trees method in parameterized algorithms. Okay. So I'm gonna tell you what is an outline of this technique. Okay. And with this outline, we'll see a lot of algorithms which use this outline, and we'll get FPT algorithms for some problems. That's the goal. Okay. So the idea of the technique is the following. Suppose you're trying to solve some problem, and say the flavor of the problem is it's kind of an editing problem. By an editing problem, I mean the problem is, say you delete a set of vertices to get something, or you delete a set of edges, you get something, or say you contract certain number of edges to get something. I mean, I'm talking about these kind of problems, okay, in general. So for these kind of problems, when we say I want to use this bounded search technique, trees method, I mean, at a very high level, I would want to do the following. Suppose I'm talking about vertex deletion problems, where the goal is to delete a certain set of vertices to get to some property, which we are trying to solve for. So the goal is, in polynomial time, try to come up with a set, some set of vertices such that this set has the following guarantee. The guarantee is there is an element in this set that is definitely there in some feasible solution. Okay? Okay, so that's the first goal. When we're trying to solve algorithms using bounded search tree methods, this is the first aim. Try to get to such a set in polynomial time. Okay, once you have got this set, what is the next thing we do? Suppose, generally speaking, suppose I have this instance that I want to solve for a given problem. There is some problem pi, and I comma k is an instance of this problem pi. And I want to solve this instance, and suppose I'm able to find such a set S, whose property is that there is always an element in S that is there in some feasible solution to this problem pi. I look at each element in S, say E1 is one element in S, E2 is another element, and say some EL, so suppose E1 to EL are the elements of S. I look at each element of this set S, and I create another instance. Suppose this instance is a graph because I'm looking at a set of vertices. I create another instance where E1 is removed. I have to talk about the parameter. E2 is removed, talk about the parameter, and EL is removed. Okay. And because I know that there is an element in S that is definitely there in some feasible solution, I know that if this was a yes instance to the problem, one of these will be a yes instance to the problem where I've removed that element and I've decreased the budget by 1. Okay. Again, what is it? This set has the property that one of the elements has to belong to the solution. Okay. So this branching is in some sense guessing which element of S will go into the solution. So I know one of them definitely goes into the solution. Suppose that element was EI. Okay. Then the claim is if GK has a solution of size at most K, then G minus EI comma K minus 1, G minus EI has a solution of size at most K minus 1. Okay. So, and hence what you do, once you find such an S, you have this instance to solve. Instead of solving this instance, you solve all these instances. And if any of these instances report 1, you say that the original instance, if any of these instances is a yes instance, you say that the original instance is a yes instance. Okay, this is the strategy. Now, since we are designing FPT algorithms, that means we want algorithms which run in time f of k, where k is the parameter, into polynomial in n. We would want to put certain constraints in the procedure so that this procedure actually gives us this kind of algorithm. Okay. So, okay. So to do so, we proceed as follows. I have to solve this instance. Instead of solving this instance, I'm saying, okay, instead of solving this, I can make recursive calls to these instances and solve them. Again, to solve each of these instances, I'll find a corresponding set, some Si in this instance, and again, I'll branch on that set Si. That's the way I'll solve it. I mean, I'm saying to solve any of the instances, I'll basically reduce it. I'll not reduce an instance unless it's very trivial. Okay. So to get to a trivial instance, I'm doing the following. I have some instance, I find such and set S, I branch on the elements of S and I get these instances. Now again, to solve this instance, I'll find a corresponding Si set which has this property in this graph, and I'll branch on the elements of that set Si. I'll get a lot of instances. If any of these instances is trivial, I'll stop and I'll tell you what we'll do. But I'm saying I'll not branch over it further. But if any of the instances is not trivial, I'm going to branch over them again. And I'm going to do it over and over again. So, if you look at the total running time of this procedure will be proportional to, you can look at this procedure as a tree. This is the root, these are its children. Then if you branch over it again, the instances that you compute are its children, and so on. So the total running time of this procedure is proportional to the number of nodes in this tree into the time that you spent on each node. Okay. So if you look at the running time, it is equal to number of nodes in this tree into time spent on each node. Okay. And again, when I say time spent on each node, I also include the time that will spend on the trivial node. So this time will, so it's basically the max of the time spent on any internal node, because for any internal node, I'll probably be pre-processing it, or I'll probably be spending time on it on some different properties, because at each node I'm interested in finding a set S and then I'll branch over it. So the time for this node, say, will be proportional to the time spent on finding such an S. And as I said, you stop branching when you get to a trivial node. So all the leaves are trivial nodes. So the time spent on all the trivial nodes would be something that, that will be proportional to the way we solve the trivial nodes. Ideally, we should be able to solve the trivial nodes very easily. So they are the special case of the problem that we're trying to solve, and they're very easy to solve. So it's that type. Anyway, so this is it. For this aspect, of the time, we would, ideally, whatever we do, not ideally, but most of the times, whatever we do, this time is usually polynomial in the input size. Okay, so we'll try to, on each node, we'll try to spend that as time that is polynomial in the input size. And again, we would try to solve the trivial instances in polynomial time. Okay, that's what we'll be doing. And now the question is, what about this? For this thing, we would try to design a procedure such that the number of nodes in this tree is some function of k. So this would, we would try to design a procedure such that this term is some f of k, where k is the parameter that we're talking about. So if we are able to design such a branching procedure where the number of nodes are f of k and the time spent on each node is some polynomial in n, we'll actually get an FPT algorithm, f of k into poly n algorithm for the problem. Okay. So this is the branching. This is the overall idea of a branch. Okay, this is also called a branching procedure. And it's a branching procedure or a bounded search tree procedure are analogous terms. So I'll just be using them exchangeably. Okay, fine. So now we are going to explore this part of the time. When I say we are going to explore this part of the time, as in we are going to go deep and see how do I aim to get a branching, what is one way of getting to a branching procedure where the number of nodes are some f of k? Okay, one way. So one way is the following. See, if I bound the number of, say, children of each node in the tree, and I bound the height of the tree. If I bound the number of children at each node of the tree by some function of k, and I bound the height of this tree by some function of k, the total number of nodes in the tree cannot be more than some function of k, right? So that's the procedure. So to get to this, to say that the number of nodes in the tree are bounded by some f of k, we'll actually be bounding two things. One is, given any node, how many branches are you going to make out of it? That's one thing. If I ensure that the number of branches that I'm going to make out of it are some, say, g of k. And then the second thing is, what is the height of this tree? So how deep am I going to go? If suppose that the height is, say, some h of k, and the number of children for each node is some g of k, then the total number of nodes in this branching tree cannot be more than g of k into h of k, right? Vaguely. I'm saying if at each node there are some g of k many children, every node branches into g of k children, and the height is h of k, then the total number of nodes in the branching tree are g of k into h of k. Okay. And I'll call that f of k. So this is like the most, I'm saying that the number of nodes in this branching tree are bounded by this, and this is like the most, I've computed this in the most naivest way. We can compute it nicely also and get some better things, but as of now, let us just focus on some f of k, some FPT algorithm. Cool. So so therefore, bounding this boils down to bounding this branching factor and this depth. Okay. To bound the depth, we typically use the following strategy. We say that, suppose, okay, first of all, let us talk about bounding the number of children. Okay. So to branch the number of children, we say, okay, suppose the set S that you have, if the size of that set is some function of k. Okay. If you're able to come up with a set which has size some function of k, this say the size of S is some g of k, and the number of children here are g of k, right? Right. So, I mean, so that's how you can bound the number of children, by always coming up with a set which has size some function of k. Okay, the second thing is bounding the height of this search tree. To bound the size of this search tree, what we can do is we can associate some kind of a measure with each instance, something. Okay, we will define what that measure means, and it's different for different problems. So okay, as of now, for the simplest case, let us say that the measure is the solution size. Okay, so for every instance, there is a corresponding solution, that the solution size that I'm looking for. For example, for this instance, I'm looking for a solution of size at most k. So k is the measure for this instance. For this instance, I'm looking for a solution of size k minus 1. So k minus 1 is a measure of this instance. Okay, so if I ensure that at every level, the measure strictly decreases, if I ensure that. Okay, so like here, for this instance, the measure was k. If you note, this instance, the measure was k minus 1. Okay, so if I ensure that at every level the measure strictly decreases, and I ensure that when the measure is non-negative, okay, I always start with the positive measure, say, that's how I do. I start with the positive measure and I say that, okay, when the measure is non-negative, the problem is a trivial problem. So you can always solve it very easily, say. That's the kind of problem that you're working with, when such that you have designed the measure, or you have defined the measure in such a way that when the measure is negative, you know how to solve the problem easily. Okay, then what is the height of this tree? Sorry, k, exactly. So the height of this tree is equal to the measure that you have chosen, right? In this case, because we chose the measure to be solution size, the height of this tree is k, because at every step the measure is decreasing by strictly 1. Okay, and hence, I mean, so obviously the problems that we'll be starting with, we'll be choosing the measure to be k, but sometimes we can choose different measure to come up with better algorithms, and we will probably see that as time comes. So the point to be noted is, it's not necessary that it should be k, because I'm happy if the height is some h of k, right? So even if, suppose there was some measure, something associated with an instance, say the measure was mu. Okay, this could be anything. Okay, I'm going to talk about very stupid things, but it can be, say, the number of cycles in this instance, say, and at each instance, say, the property is that at each suppose at every level the property is that if the number of cycles here was mu, then the number of cycles here are strictly less than mu, say. And you know that when the number of cycles in the graph are negative, which basically means nothing, it just means that, okay, if the graph is cycleless, you know how to solve the problem. That's a trivial instance, and you know how to solve the problem in polynomial time. Even then you are fine, right? But okay, in that case, what will the height of this tree be? It will be mu. Okay, I mean, I just started with any arbitrary measure. The point is, if the value of this measure is a function of k, again, even then it is fine. So if this was equal to some h of k, then also the height of this tree will be some h of k, it will be some function of k. So all I'm saying is, you need not start with, the measure need not only be the solution size, it could be anything, but that anything, the size of that anything is bounded by some function of the solution size. Okay, so this is how we'll try to bound the size, height of these branching trees. Okay. Fine. And this is pretty much all about this technique of bounded search trees. So this is all. So you have a problem to solve. In polynomial time, you try to find this set S of vertices. You have some instance, say, I'm talking about graph problems. I have an instance g comma k, and I find this set S for this instance g comma k. The property of that set S is any solution to whatever problem we're trying to solve in G, there is an element of S that is definitely there in some solution. I branch on the elements of S and I get to these many instances. If any of the instances is a trivial instance, I stop. I stop as in I don't branch further. But if it is not, then again for this instance I find a corresponding set, some Si or S prime, and I branch on the elements of that S prime and get a lot of instances, and I go on doing so unless I'm left with trivial instances. Okay, and once I have done that, and once I cannot branch any further, I know that all the leaves of this branching tree are trivial instances. I can solve the leaves of the branching tree in polynomial time, because I mean that's how we have defined the trivial instances. The trivial instances can be solved in polynomial time. You solve the trivial instance in polynomial time, and if even one of them is a yes instance, we conclude that the original instance was a yes instance. Okay, and how do we conclude that? Because of this property of S. Because if not, suppose one of these instances was a yes instance. If suppose even after then, even then, if this was not a yes instance, then what could go wrong? Suppose there was some leaf. Say it was this leaf that was a yes instance. Okay, if this leaf was a yes instance, that means so it's like this leaf is some graph G prime, comma, some parameter L. If this was a yes instance, that means there is a solution of size L in this graph. And the way I would have come to this instance is by saying that I would have branched on some element which is one of the vertices in this graph G that I have here. So this is G double prime, so this is G that I have here, and this was L plus 1. The claim is if look at any solution of size L here, then that solution union E1 is a solution for this graph. And because the solution here had size L, the solution here will have, that solution union E1 will have size L plus 1, and hence this is a yes instance. Similarly, you just traverse this path from this leaf to the root. If you traverse this path, we get, if this was a solution here, then if this was a yes instance here, then what? The root is also a yes instance. Okay. And similarly, the other way around, if the root was a yes instance, then we know, the way we are branching, we know that there is definitely some solution that contains one of these elements. Okay, and if there is definitely one solution that contains one of these elements, suppose, and I mean now what are we going to do? We're going to do to prove the forward direction, we're going to do the following. Suppose this is an instance at the root, and there is, so if it's a yes instance, there is a corresponding solution at the root. Because the property of the S is the following, that there is some solution that contains one of the elements of S, you look at that solution. So this solution will definitely contain some E prime, E1, EIs are these things. A solution here will definitely contain some EI from there. If it contains EI, you go to the branch that is labeled by EI. So every branch say is labeled by the element that I'm picking in the solution. You go to that branch. Then if this was a solution to this graph, then this solution minus EI is a solution to this graph. Okay. So, I mean, this is the general flavor of the technique that I'm talking about. Of course, there are a lot of things, okay? Things like the problems that we're talking about should be hereditary and all those things. For example, I mean, the problem should be of such a flavor that if this is mostly these graphs will be some sense subgraphs or say minors of this original graph, and hence you should be able to transmit the solution to this for this instance to this instance, and the kind of problems that we'll be seeing, or the kind of problems which will be applying bounded search tree methods, you'll be able to do so. Okay, I mean, okay, so let us do one problem formally, and let us see everything in a formal setting. So let us talk about this problem called vertex cover. I hope you all know what this problem is by now. It's removing a set of vertices such that the endpoint of every edge, there is at least one endpoint of every edge that is there in the solution. Yeah. Okay. So now suppose I want to design a bounded search tree algorithm for vertex cover. Okay. Again, let me just write the problem. What is a vertex cover of the graph? A vertex cover of the graph is a set of vertices such that for each edge in the graph, one of its endpoints are in this set. Okay. So now our parameterized problem is that we're interested in finding, given a graph G and an integer k, we're interested in finding whether the graph G has a vertex cover of size at most k or not. And I want to do it in f of k into poly n time. Okay. Fine. So again, I'm given this instance G comma k. Okay. And I would want to find such a set S of vertices which have the guarantee that there is at least one element in S that is there in some feasible solution, and I would want to branch on this set S. Okay, that's the first step. Let us do the first step and then see how we proceed further. So what could possibly be a set S in this framework of a vertex cover problem? Sorry? So I'm saying this is a vertex cover problem, and this is the instance that I'm starting with. Now I want to branch somehow on this instance, and what is that somehow? I want to come up with a set S of vertices which have the property that there exists an element in S that is there in some feasible solution. What is a feasible solution in our case? That means that is there in some vertex cover of size at most k. Right? If I'm able to come up with a set of vertices such that there is always an element of S that is there in some feasible solution, that is there in some vertex cover of size at most k, I'll branch on that set S. Okay. So what could be such a set S for this instance of vertex cover? Sorry? So vertices with max degree, as in you want to say that if there are vertices, okay, yes, vertices with max degree means? Okay, suppose the max degree of the graph is say 5, something like that. Okay, so you're saying let us sort the vertices of the graph in the descending order of their degrees. Okay, then that's S. So basically S is the whole largest degree. Okay, so suppose the largest degree of the graph is say delta. You're saying S is equal to all those vertices such that degree of V in G is equal to delta, where delta is the max degree of G. Okay, so your claim is that there is always a solution that contains one of these. I mean, it is possible is one thing, right? So okay, so when we are doing these kind of things in theory, what we want is that there is definitely, it's definitely true. I mean, of course, if I was doing some maybe for all practical purposes, this almost always happens. But when we're doing it in theory, we're not worried. We're not talking about almost cases. We're like, this should definitely happen. Okay, so that's why. I mean, suppose something. I mean, say. Okay, so for example, this is a vertex of degree 5, say, okay, and yeah, I think maybe this, or we can consider a smaller example. So suppose this is the graph, okay, so what is the max degree of this graph? 5. So your S will contain this vertex V, okay, so this is your S. S has only one vertex, and that is V. So, and what are you claiming about that set S? So, what I'm saying is, you can't claim that property about that set S. What is the property? The property is that there is always an element in S that is there in some feasible solution. And feasible solution as a solution of size at most k. And suppose for this problem, say, my k is, this is my graph G, and my k is, say, 5. Is there a solution vertex cover in this graph of size 5 which contains V? No, because the only vertex cover, say, in this graph of size 5 is that contains all these vertices, right? So it's not always true, vertex cover. So yeah, not this, but let us talk about even elementary. I mean, let us go to the definition of vertex cover and see what can it do. What is the definition of vertex cover? It is a set of vertices such that for every edge, one of its endpoint has to be in any solution. Right? This is the definition of vertex cover. So does this tell you what could possibly be is? Again, for every edge, look at any edge in the graph, say this edge, any edge in the graph, say UV, one of its endpoint has to be in the solution. And what was S? S was also a subset of vertices such that one of the vertices have to be in the solution. Okay. So basically the claim is, say, let us see if you see this. The claim is for this instance G comma K, and S, a possible S could be, look at any edge in the graph G. Any edge. And let that edge be, say, U comma V. So these are the endpoints of that edge E. The claim is UV is that S that I'm talking about for any edge. So there could be a lot of S for a particular graph also. You can branch on any given S, any S. Why? You see that why? Right? Because the thing is, one of the endpoints have to be there in any solution, right? So I can branch on this set S. So a set S for vertex cover is, look at the endpoint of any edge. Fine. So I'm going to branch on U and V. Okay. And what does it mean when I say I'm going to branch on U and V? We know that one of these vertices are there in the solution. Okay. When I branch on U, it's like assuming that U is in the solution. When I branch on V, it's like assuming that V is in the solution. So whatever I do in the following branch, I'll assume that U is in the solution. Whatever I do in the following branch, I'm under the assumption that V is in the solution. And what I know that one of my assumptions is true. So if this one is true, eventually, I mean, this branch will make no sense for me, but I'm anyway going to discard it. But right now, I don't know which assumption is true, so I'm going to branch on both the cases. Okay. So now, when I'm in this branch, just assume someone came and told you that U is there in the solution that you're looking for. Okay. Now we're solving the vertex cover problem, and someone tells you that U is definitely there in the solution that you're looking for. What will you do with this kind of a vertex? So basically now we want to come up with some other graph where the parameter is, say, decreased. Okay. And in this case, the branching algorithm that I'm defining, the mu that I was talking about, it's the solution size as of now. Okay. So what do I want? Because I want to eventually bound the height of this tree and also the number of branches. The number of branches are anyway gonna be bounded because at every step, the way I'm gonna get to S is by looking at any edge and its endpoint. So there are only 2 branches. So constant number of branches, fine. Hello? Hey, hello, is it disconnected? No, not yet. Hello, can you hear me?
No, I think disconnected.
Yeah. Should I do something? Cool. So, and hence, okay, and now I'm saying, suppose I know that this vertex is going to be in the solution, and I'm talking about the vertex cover problem now, okay? My claim is, if you know this is going to be in the solution, just delete that vertex from the graph and reduce K by 1. What does this step mean? This step should mean that, okay, if this is a yes instance and you are assuming that, or in fact assuming, or suppose you're trying to find out a solution, a vertex cover in this graph of size at most K, which contains U, if this is what you're trying to find out in this graph, then this instance is equal to this instance of vertex cover. This instance of vertex cover says that you're supposed to find a vertex cover of size at most K minus 1 in this graph. Okay, this is what. And it's easy to see that this instance is equivalent to this instance under the assumption that the u is in the solution that you're trying to find out. Okay, fine. And similarly, for this branch, we'll assume that v is in the solution and we'll branch. Okay, and what are we gonna do? Suppose we are gonna repeat it for every instance. We're gonna find an s like this, and we're gonna repeat it. Okay. So now, when do we stop? As in, what is the notion of a trivial instance for me? One thing which we definitely want is the following: that the trivial, that whenever k becomes negative, you should definitely be able to stop and infer something from there. Okay, that's one thing. So whatever is your trivial instance, I mean, so those kind of instances for which k is strictly less than 0, they should definitely be your trivial instances, and you should be able to tell them or solve them in polynomial time. Okay, so let us see what happens when k, so suppose I go on branching until k becomes 0, say. So because see, now in this case, note that in each branch I'm decreasing k by 1. So it will not directly jump from being totally, I mean, non-negative to non-positive. So it will hit 0 somewhere, right? Definitely. So that's one thing, and we have to talk about other issues also. So for example, what happens when k becomes 0? So you have a graph G and k is 0. And what are you interested in? You're interested in finding a vertex cover of size 0 in the graph, in this graph. Can you trivially solve this problem? You have a graph G. The question is there a vertex cover of size 0 in the graph? Okay, if suppose yes, suppose this was a yes instance. If there is a vertex cover of size 0 in the graph, then what does it mean? So if suppose there is even one edge in this graph, then can there be a vertex cover of size 0 in this graph? No. So basically I'm saying checking whether the graph has a vertex cover of size 0 and or not is equivalent to checking whether the graph has an edge or not. Because if the graph has an edge, it cannot have a vertex cover of size 0. And if the graph has a vertex cover of size 0, then it cannot have an edge. Okay. So when k is equal to 0, you just go and check whether there is any edge in the graph. That will take some polynomial time, right? Just go through the edge list. Not even go through the edge list. Some constant time. Just go, start, look at the edge list, and if there is even one edge, if you find even one entry, you know that there is an edge in the graph. So when k is equal to 0, you know how to solve the problem, right? So definitely the tree won't so the height, so definitely the height of the tree is k, right? It cannot be more than k, because you started with k, and each step, if you see, you're decreasing the parameter by strictly 1. So the height of the tree is at most k. Okay, so there are of course other things that you have to, when you're writing it down properly and nicely, there are other things that you have to take into account, like maybe k is not 0. See, we are always branching on a set S, and that set S is what? It's the endpoints of an edge E, right? So at every instance, you should be able to find such a set S. What if you cannot find such a set S? Then what do you do? Then also you should be able to say that, okay, even then I'm able to solve the problem efficiently, right? For example, in this case, if I'm unable to find such a set S, what does it mean? Or when is it that I'll not be able to find such a set S? Yes, again, when there is no edge. So even when I'm not able to find such a set S in my graph, that means there is no edge, and that means the graph is an independent. I mean, and then again, for those instances also, for which you cannot find an S, that means you cannot branch further, you are able to solve this problem in polynomial time, right? In either case, the point is the height of this tree will not be more than k, okay? Because it's like maybe I stop earlier, maybe I don't even go till k height, but maybe I stop earlier because I'm unable to find S. But even if I go deep down, I'll definitely not go beyond k equal to 0, because then I'll like brute force and I'll interrupt and just stop when k is equal to 0. Okay. So this is an algorithm for vertex cover. Note that the height of this tree is at most k. The number of children of this is 2, and what? And at each node, how much time are you spending? If they are trivial nodes, or say trivial nodes, or the leaves, say, from where you're not branching further, you are only checking whether the graph is an independent set or independent graph or not. That takes some, say, polynomial time. Okay. Otherwise, if it is not, then what are you doing? Then again, at every node you're checking whether there is some edge in the graph or not, because if there is some edge, you're going to branch on that. Again, even that takes polynomial time, right? So you are indeed spending polynomial time on each node, and the number of the nodes, I mean, and the tree is like this. The height of this tree is k, and the number of, and at each branch, so you're branching into 2 cases at every node. Okay. Yeah, I think I very stupidly wrote that g into k. It should be g power h of k. Why? Because it's like gk children going, and from each of them again gk things going, and up to a height of h of k. But anyway, we'll see that. So this is the branching tree that I get corresponding to vertex cover, and the running time of the algorithm is the size of the number of nodes in this branching tree into polynomial n in n. Okay. Okay. So now, okay, so now whenever we do this formal analysis of the size of the branching tree, we can always get vaguely, we can get this is like, we can get some vague analysis, but as we'll see further, we'll try to get algorithms that have running times that is strictly better than the naive running times. And sometimes it's just because, we are solving, we're trying to compute these number of nodes in a better way. And what is that better way? Note that to compute the number of nodes in this branching procedure, we typically proceed as follows. First of all, note that every node, if there is any if there is any node in the branching tree, then it has 2 children. So whenever we branch in more than 2 we branch in more than 1, 2 or more branches. Okay. So for at least for this case, see that we are always branching in 2 cases. We never branch in 1 case. Okay. So every internal vertex has at least 2 children. Now just recall that in a tree, if you have a tree where every internal vertex has at least 2 children, then the number of internal nodes, or if the number of leaves in that tree is bounded by, say, L, then the total number of vertices in that tree are 2L minus 1. So basically, if the number of leaves in such a tree are bounded by L, then the total number of internal vertices cannot be more than L minus 1, and hence the total number of vertices in that tree are 2L minus 1. Okay, this is a standard graph theoretic result, and it's very easy. You can prove it. So it's just that if you give me a bound on the number of leaves in such a tree, I know the total number of nodes in the tree are bounded by this number. Okay, so to compute the total number of nodes in such a tree, we'll just be interested in computing the number of leaves in the tree. If we compute the number of leaves, we are done, because the total number of nodes will be this then. Okay. Now to compute the number of leaves in the tree, we'll write recurrences. Okay. So say for this problem, say Tk denotes number of leaves in, say, this graph in G for this instance. Okay. Then I want to suppose the number of leaves in this graph is denoted, if for this instance is denoted by Tk, and to solve this, the number of leaves, if the number of leaves here are Tk, then we know that the number of leaves in this in this branching tree rooted at this node, if they are some Tk, then Tk is equal to the number of leaves that are rooted at the branching that are there in the tree which is rooted at this node, plus the number of leaves that are there in this tree that is rooted at this node, right? Again, I'm saying I want to compute the total number of leaves in this whole branching tree, right? So this is the root of the branching tree, okay? So I'm saying that if the total number of let me call the total number of leaves in the branching tree to be some tk, then this tk, basically the number of leaves in this branching tree is equal to the number of leaves here plus the number of leaves here, right? And that's all that I'm saying, that if the number of leaves here are denoted by tk, then this is equal to the number of leaves that are here. By here I mean that are there in the subtree. This is a tree and this is one subtree that is rooted at this node, and look at the subtree that is rooted at this node. So that subtree is this subtree is this, okay? So it's this plus this. And if I have to write a recurrence, we typically write these recurrences in terms of mu. So mu was, remember, mu was the measure that we would have associated with the branching tree. So in our case, mu is nothing but the solution size. So if tk were the leaves here, note that this instance has k minus 1 as the measure, this instance is k minus 1 as the measure. So I can write this as okay. And when the measure has dropped down to 0, okay, we know that the number of leaves in that subtree, when the measure has dropped down to 0, is 1, because when the measure has dropped down to 0, that's a leaf. That's a leaf node, right? And if you just look at the tree rooted at that leaf node, which is nothing but that node itself, the number of leaves in that is 1. So this is the thing that you get. And then now you just solve this recurrence. Okay. Again, the point of writing it like this, writing a recurrence in terms of k or the measure, was the following: that if you look at two instances, see, we stop when the measure becomes 0 or the measure becomes non-negative. For this problem, we are stopping when the measure becomes 0, right? When k becomes 0, or maybe earlier. And hence, if you look at the number of leaves at any point of time, it's function of the measure. In the sense that, I'm trying to motivate why am I putting k here, okay? It's like if suppose the instance is measure k, then suppose it has these many leaves, then I'm trying to say, okay, now if the instance is measured mu k minus 1, then it has these many leaves, and if the instance is measured k minus something, it has these many leaves. And I want to say that if the instance has some measure, the number of leaves is this, you can write it, the number of leaves in this instance, you can write it as a sum of the number of leaves here and the number of leaves here. Again, one important point is that the measure is strictly decreasing at each level, right? And hence, if you look at this thing, if you look at the number of leaves which correspond to this tree, which has a particular measure, say k, it can be written as this leaves plus this leaves, and we know that the measure for this instance is strictly less than whatever was the measure here, and the measure here is strictly less than whatever was the measure here. So basically, we can write this recurrence. Now the point is, we have to solve this recurrence. Okay. For this recurrence, I think all of us knows that this is like, this recurrence will solve to 2 power k. Okay. And hence we know that the number of leaves here are bounded by at most 2 power k, and hence the total number of vertices, total number of nodes in the tree are also bounded by some order of 2 power k, and hence the running time of this algorithm is order of 2 power k into poly n, because of this. Okay. So now, yeah. So this is one algorithm for vertex cover that runs in 2 power k poly n time. Now what we're going to do is we're going to see a slightly improved algorithm for vertex cover using the same technique. The technique is the following. Note that we know that this recurrence solves to 2 power k, And note that we also know that, okay, if any of this value, like this is 1 here and this is 1 here, if any of these values was more than 1, then this recurrence will solve to something that is strictly, it will solve to something that is strictly less than 2 power k. This will solve to something like c power k, where c is strictly less than 2. If any of these numbers is strictly more than 1. So if the drops are more in any of the sides of the recurrence, then this recurrence will solve in something that is strictly better than 2 power k, and we're going to exploit that to get a better algorithm for vertex cover, because we know that the running time of our algorithm is nothing but whatever recurrence we write, whatever this recurrence solves to, into polynomial in n. So we are going to try to write a better recurrence. And how can we write a better recurrence? To write a better recurrence, see, where are these things coming from? These things are coming from the fact that the instance that you created here, the measure for that instance was k minus 1, and again the instance that you created here, the measure of that instance was k minus 1, and hence is k minus 1 into k minus 1. But suppose, given this instance, I can reduce it to instances where the measure drops was strictly more than k, say. Okay, then suppose this was some, say I can make sure that this is something like k minus 2. Then the recurrence here will be tk is equal to tk minus 2 plus tk minus 1, and this is a better recurrence than tk minus 1 and tk minus 1, and hence this will definitely give us something better than 2 power k. This is the aim. Okay. To get an FPT algorithm, it was enough that the measure decreases by at least 1, but now we are trying to get improved algorithm, so we would want that the measure decreases by as much as possible. Okay. Okay. To do this, what we can do is, there are a couple of things that we try to do for general problems. Some things are, we try to pre-process the graph, okay, and these are very abstract things. Okay, when you see problems and you see their explicit algorithms, you'll see what I mean then. But in a very broader sense, you try to pre-process the instance, and then this pre-process instance has some nice properties. Okay, and the nice for example, suppose you are able to pre-process your instance. When I say pre-process, as in you do something with the instance and you get to a new instance which is equivalent to the previous instance. Equivalent, by equivalent as in, if that was a yes instance and this is a yes instance, if this is a yes instance then that is a yes instance. So you pre-process it to get to an equivalent instance, and during pre-processing you'd spend time that is polynomial in the size of the input. So that's just polynomial time. And now the good thing is, this pre-process instance has certain nice properties. For example, say that you were able to pre-process your given instance and get to an instance where the minimum degree is, say, at least 2. Say, I gave you an instance g comma k of vertex cover. You were able to do something with the instance and come up with another instance, say some g prime comma k prime, which is an equivalent instance. Equivalent as in, if that gk was a yes instance of vertex cover, if and only if g prime k prime is a yes instance of vertex cover, and you were able to do this transition from gk to g prime k prime in polynomial time. Say, so this much I gave you. You were able to do this, and the good thing about this instance g prime comma k prime is that in g prime the minimum degree of any vertex is say 2. So no vertex has degree 1. Say you were able to do that. Then let us see, how can we get a better branching algorithm for that problem? Again, so now what is it that we have? Again, there is some edge UV in your graph. True. Again, your set is S, and you're going to branch on, okay, in this case, we'll see that, okay, we'll see a different kind of branching now, okay, and let us just see what it is. So now again, there is an edge UV, and you know definitely either U goes to the solution or V goes to the solution. You know for sure. Fine. Okay. But we know that every vertex has min degree at least 2. Every vertex has degree at least 2, because the min degree of the graph is at least 2. Okay. So say there is this vertex U and it has some 2 neighbors, say V1 and V2. Okay. Fine. So now again, we know that, okay, so now compare this to the case when you just had an edge. When you just had an edge, you knew that if U doesn't go, then V has to go. But here you have more information. What information do you have? You have that, okay, if u doesn't go to the solution, then both v1 and v2 have to go to the solution. Why? Because any vertex cover, you look at any edge in the graph, one of its endpoints has to go. So if u doesn't go, the other endpoint has to go, which is v2, and if for this edge, and if u doesn't go, this end for this edge v1 has to go. Okay, and hence if we know this, that in your graph you have that every vertex has the degree of every vertex is at least 2. What you'll do is you look at any vertex, you say that is u, look at its neighbors, there are at least 2 neighbors, there could be more, right? But we know there are at least 2 neighbors. Okay, and then how do you again, that was just the motivation of starting. But now if you notice, branching is just that, it's like saying that, okay, either this case will definitely happen or that case will definitely happen. So depending upon how many ways you branch, it says that, okay, one of these ways would definitely happen. That's the idea. So again, here one thing is u belongs to the solution. If u belongs to the solution, well, fine, good. But if u doesn't belong to the solution, we know that definitely v1 and v2 both should belong to the solution, right? And hence in this case, how we are going to branch like this. In this branch, we are going to say that, okay, u belongs to the solution, and in this okay, so see, with every branch, as we said, we have some assumption associated. Like in this branch, we have the assumption that u is going to be in the solution. Assume that u is going to be in the solution and proceed. For this branch, the assumption, basically you can think of the assumption being that u is not belonging to the solution. So one of these things will definitely happen. In the previous case, we know that when u didn't belong to the solution, then v has to belong to the solution, right? This was a corollary. V belonging to the solution was a corollary of the fact that u didn't belong to the solution, right? And hence we could create this kind of an instance. Similarly, in this case, u not belonging to the solution helps us deduce that both v1 and v2 should belong to the solution. So if u doesn't belong to the solution, we know v1 belongs to the solution and v2 belongs to the solution. And hence in this case, we can create an instance which is g minus v1 v2 comma k minus 2, right? And now again, to bound the number of leaves in this tree, we'll write a recurrence, and in this case the recurrence will be k minus 1 plus k minus 2 equal to 1. Okay, and if you see how we solve this, if we solve this recurrence will actually be, we can actually solve this recurrence in maybe 1.6181. Yeah. Sorry? Yeah, this is the golden ratio. Yes. Okay. And of course, this is better than 2 power k, right? So that was 2 power k into poly n. This is 1.618 power into poly n. Okay, is this clear? But again, we are under the assumption that I can pre-process my graph so that the minimum degree is at least 2. But suppose I am able to do this, then this is clear, right? Okay. And now, can you make the pre-processing statement realistic? I mean, so I said assume that you can pre-process it, but can you really pre-process the graph to make the minimum degree at least 2? How? So what do I mean? I mean, okay. Sorry?
Get rid of all the leaves by picking the neighbors and deleting.
By picking the neighbors and deleting them. Okay. So you've all seen a kernelization algorithm for vertex cover, right? Okay, maybe not you, but you've all seen the kernelization for algorithm for vertex cover. So there was a reduction rule that got rid of degree 1 vertices, right? What was the reduction rule saying? That, okay, if you have a vertex of degree 1, you apply that rule. I mean, whenever you have a vertex of degree 1, you apply that. You have a reduction rule and you apply that reduction rule. Okay, and eventually, when you are not able to apply that reduction rule, you know that there is no vertex of degree 1. So every vertex has degree at least 2. And note that what is the property of a reduction rule? It works in polynomial time and it gives you an equivalent instance, right? So you can do the same thing. We'll talk about it. Okay. So you can do the same thing here also. You are given an instance, and suppose there is a vertex of degree of 1. Then you apply that reduction rule, get rid of it, you come up with an equivalent instance. Again, if there is a vertex of degree 1, you go on doing it. And if you're not able to do it, you know that your instance has minimum degree at least 2. Okay. Still 1 minute. Okay. Hello? Can you hear me? Okay. Hello? Yeah. Okay. So this is one way. One way of so this is pre-processing is one way. You can pre-process the instance to get to an instance that has certain nice properties, and you can try to exploit those nice properties in the branching algorithm. Okay. And see, this gave us t into k minus 1 plus t into k minus 2. Again, I've not told you how do you actually solve the recurrences, but I mean, as of now, just believe me that this recurrence solves to this. Okay. Now, one last thing quickly. Again, another way of improving the running times is also the following. It's like, okay, so what did we do here? We said that, we said that we had a graph. We could pre-process the graph so that the minimum degree of the graph is at least 2. Okay. Now again, suppose the minimum degree of the graph is now we are trying to be like. So suppose now that I'm able to pre-process the graph or do something, and suppose I know how to solve the case when the minimum degree of the graph is at least 3, say. At least 2 we know, right? If it is at least 2, I get this. Again, so see, if we improve these recurrences, we know we'll get better running times. Okay, so now the aim is to improve it as much as we can. Okay, so if you're improving it along this line, and this line is this minimum degree line, if I knew that, see, if I know that the minimum degree is, say, some L, then this recurrence will be k minus 1 plus t into k minus L, because here I'll remove all those neighbors, because if u doesn't belong, then none of its neighbors will belong, right? So on that note, now suppose, can I somehow ensure that if G has, say, min degree at least 3, then I would want to use the branching algorithm. Okay. If not, I mean I don't want to branch if the minimum degree of the graph is less than 3. That's what I want to do. Okay. If I know that I'll only be branching when the minimum degree of the graph is at least 3, then I know now in that case I'll get a recurrence that has running time t into k minus 1 plus t into k minus 3, and this is definitely again better than this. Okay. So again, I want to do this. If the minimum degree of the graph is at least 3, then I want to branch. Otherwise, I don't want to branch. Okay. And one way that we saw was, again, we can try to pre-process. We can try to pre-process the graph so that the minimum degree of the graph is at least 3. Okay. One is that thing. Another thing, maybe you can do that also, but I'm just trying to tell you another way in which we can achieve this is, you can put the other constraint in the trivial. I mean, maybe, see, there can be two, like, there are a lot of things that can be there, but amongst them, 2 of the things are the following. Maybe you are able to pre-process the graph so that the minimum degree now becomes 3 in the graph, and you are only branching on this graph now, which has minimum degree 3. Or maybe you are not able to really pre-process the graph, but what you do is, you do the following. If there is a vertex of degree 3, say 3, then you branch on that vertex. So you only branch when there is this vertex u of degree 3. In that case, whenever you branch, you know that you will get this recurrence. Okay. But now, so if you're always able to find such a vertex, you branch. Now when you're not able to find such a vertex, what does that mean? The graph has min degree at most 2, right? So I'm saying, if the graph has min degree at least 3, then you branch. And okay, no, let me not write it like this. Let me write it like this. If G has a vertex of degree at least 3, then you branch. Okay. So now whenever you branch, we know that k reduces by 1 here and k reduces by 3 here. Okay. Now when you're not able to branch, what does that mean? That otherwise we know that min degree of G is at most 2. Okay. Sorry, max degree. Maximum degree of G is at most 2, because otherwise if it was not 2, there was a vertex of degree at least 3 and then you would branch on that vertex, right? So when I'm not able to branch, I know this is the case. Okay. See, if I can solve this case in polynomial time, then this will correspond to my I can say that this is my trivial instance. So I'll not branch ahead of it. This will be my leaf then. Okay. So now, so that's the second thing that we try to do. Maybe we can pre-process to get to this condition, or maybe you can try to solve. Maybe the other condition is so trivial that you can just, I mean, if you get to that condition, that becomes your leaf of the branching tree. You do not branch further. Instead, you just solve the problem trivially. Okay. So let's see. If suppose the max degree of the graph is at most 2, then can you solve vertex cover in such graphs trivially? For that, we just need to understand how does graphs of maximum degree at most 2 look like. So the claim is, if the max degree of a graph is at most 2, then that graph is nothing but a collection of cycles, paths, or isolated vertices. So the graph is like some cycles of arbitrary length, some paths, maybe a lot of cycles, a lot of paths, and a lot of isolated vertices. So if the max degree of the graph is at most 2, then this is how the graph looks like. And can you see that in such graphs you can find the vertex cover, say the minimum vertex cover easily? Because for a path you have to pick every alternating vertex, right? And so is with cycles, depending upon odd or even cycles. So you know how to solve the problem easily, right? In polynomial time. So and hence you can do this. So what have we done for this case? If in the graph there was a vertex of degree at least 3, you branched on that vertex. And when the graph doesn't have a vertex of degree at least 3, we know that the max degree of the graph is bounded by at most 2. And hence you are in this case and you can solve this problem easily in polynomial time. And this is your trivial case now, the trivial node now. And hence, if you look at the number of nodes in this branching tree, it will be the recurrence for that will be tk minus 1 plus tk minus 3, because it's 1 and minimum degree is 3, so there will be at least 3 neighbors for sure. And if you don't pick you have to pick all those 3 neighbors, and hence k decreases by 3. This is when you're at the 0 thing, the number of leaves is 1. When k is 0, the number of leaves is 1. And this solves to, I forgot. Yeah. So tk minus 3 solves to 1.4656 par k. Okay. Again, if you solve this recurrence, it will solve to this. I'm not going into it right now. And this is strictly better than that. And again, so basically what have we concluded? We have concluded that the number of nodes in this tree is order of this. Okay. And now the time spent on each node, again, for each internal node, the time spent is the same, because you just, okay, the time spent is the times that you need to look for a vertex of degree at least 3. Okay, in that case, basically, you just look for a vertex of maximum degree and branch on that vertex. So that's polynomial time. Again, for the trivial nodes, again, it's time taken to solve such instances, and we know such instances we can solve it in polynomial time, because you have to pick every alternate thing in each of the disconnected pieces here, right? So it's again polynomial time. So it's polynomial time into 1.4656 par k. Okay. So cool. So this was for vertex cover. Again, right now in literature there are algorithms for vertex covers that have running time better than this, but I mean, again, they use some other properties. By the properties I mean, you cannot really hope to do this. I mean, you cannot hope to go on this line. This line is, you cannot say that, okay, if G has a vertex of degree at least 4, then I'll branch. Otherwise, max degree of the graph is at most 3, and you can hope to solve it in polynomial time. We cannot hope to do so. Why? Because vertex cover on graphs of maximum degree at most 3 is NP complete. So if the max degree of the graph is at most 3, we cannot hope to solve vertex cover in polynomial time. and hence I can't try to do this. But this is not the only way in which you can hope to get better algorithms for vertex covers. There are other ways, other observations, which probably maybe you'll see, to get better algorithms for vertex covers, and using those kind of things, you can definitely get better than this. So there are definitely better algorithms than this. But so this was one way of getting better algorithms for vertex cover. Okay, so we end the class here now. So hopefully Venkatesh will continue tomorrow with whatever he plans to. Yeah. Thanks. Thank you.